Page 91. Oh, by the way, how did the metric conversions go? Were they okay? The metric conversions, how did the metric conversions go? They're pretty good? Okay. I'd like to do a metric conversion quiz on Monday. Can we do that? Metric conversion quiz Monday? Monday, let's see, 17 plus 7 is 24. Because you can practice today and tomorrow. Like today is like Tuesday, that's like 6 days away. You have 6 days to practice. Okay, that's what we call wishful thinking. I'm sorry to burst your bubble. That's a sad thing. All right, 4 types of particles. We're not including subatomic particles here, which of course are the protons, neutrons, electrons. We're just talking about things that are like, you know, atom-ish size. Okay, so we have obviously atoms. And if we look at them, what is their charge? What is the charge of an atom? 0. Atoms are neutral. Okay? Now, how about that molecule? What is the charge of our molecule? Neutral. And then we have some ions. And ions can be either what or what? They can either be positive, in which case they are called cations. Have we talked about how we know that cations are positive? The T looks like a positive sign, and also cats have pos. Okay, cations are positive because cats have pos, or because there's a plus sign in the middle of cation. And then the negative ones are anions, because it sounds like onions, and onions make you cry. Or you can remember a negative ion. A-N, a negative ion. And then finally, we have this new one that you may or may not have come across. And this is called a formula unit. It is neutral, but it is made of ions. Okay? It's like a molecule for an ionic compound. But we can't call it a molecule because molecules are only between nonmetals. Okay? So we have this formula unit thing, which is a single unit of an ionic compound. We have ions, which are either positive or negative, and they will always say their charge. Whenever you write an ion, whenever you write a symbol for an ion, it has to say the charge because if it doesn't say the charge, it's not an ion. We also have molecules. They are neutral and they are made of neutral atoms. And if formula units are for ionic compounds, what are molecules for? They are for covalent compounds. Or covalent elements. Like H2 or O2, something like that, where the O is bonded to the O, right? That's not a compound, it's a element because it's just oxygen, O2, but it is a molecule because there's two particles, okay? And then of course there's just the plain old atoms, which are just hanging out, being really boring and neutral and not really doing much at that point, okay? So an atom is the smallest component of an element. They can be metals or they can be non-metals. And do you remember your staircase on the periodic table? Is this ringing bells? Kind of. What you do to draw the staircase is you start up at the corner of boron and you go down, and then you go across, and then you go down, and then you go to the right, and then you go down and to the right, and down to the right, down to the right, down, and then we're done. Everything over on this side is nonmetals. And everything over on the other side is metals. Except we have one funny one. Hydrogen. Hydrogen is a nonmetal. A no metal. Oh, I need an N in there. And how about these guys at the bottom here, this little funny rows, these couple rows down at the bottom? Those are also metals. And you can see on, even though you don't maybe have the lovely blue color, you should have things that are gray and things that are colored in white. And so the gray ones are the non-metals and the white ones are the metals. Now, yes, there are metalloids in there, but we're not going to worry about those four today. Can we just do that? We'll just say metalloids, pretend they don't exist, okay? Everything to the right is a non-metal. Everything to the left of that staircase is a metal. Now, if you have an element, and that element is a metal, it's made of metal atoms, okay? And they arrange themselves in very regular three-dimensional structures. This is a metallic crystal. Do we know that word? Starts with an L. Lattice. But the difference is that in an ionic crystal lattice, you had alternating positive, negative ions. Instead of having alternating positive, negative ions, you just have neutral atom, neutral atom, neutral atom. They are all neutral atoms. So that's what metals are like, and they are all solids at room temperature, except for one. Yeah, mercury is the exception. Mercury is a liquid at room temperature. And so you can see these are neutral mercury, Hg, atoms, but they no longer have that regular structure. They're now flowing past one another. There we go. So those are our metals. They're all solid at room temperature except for mercury. Sorry, I got a cough drop in my mouth now. So if I sound funny, that's what's going on. All right, non-metals. Non-metals, some of them are gaseous, but others are liquid, and others yet are solids. And it really depends, like there's much more variation. Like metals all pretty much look like this, yeah? But non-metals, this would be an example of a noble gas, okay? Where we have, whoops. Where we have individual atoms. But some of the others, they don't exist as individual atoms. Can you think of an element that does not just look like single atoms? Oxygen, right? Oxygen is not monatomic. What does mono mean? Mono equals 1, okay? So if you're monatomic, you have one atom. And really, it's only the noble gases that exist as monatomic gases. So those are atoms. Now we're going to move from atoms into molecules. If you recall, the molecules are neutral. And molecules are all made of nonmetals. So if you have a molecule, it's just going to be these elements, the ones that are to the right of the staircase. Plus hydrogen. Okay. But if you have a molecule, it has to be 2 or more atoms, and they have to be bonded together covalently. So molecules are covalent. If you have 2 atoms that are stuck together with a covalent bond, what do they do with their electrons? They share their electrons. Okay? Now there's 2 types of molecules. You can have molecules that are elements where you have only one type of atom. That would be like, for example, O2. Or you can have elements which are compounds. And if you have a compound, that means you have two or more types of atoms. So that could be like H2O, for example. Where you have both hydrogen and oxygen. One of my favorite questions to ask is, are all molecules compounds? Because it really tests whether you know the difference between the word molecule and the word compound. Compound try to define the word compound to your partner. See what you can do, just based on your prior knowledge. Diatomic elements are not compounds. So a compound is a pure substance, even though it's made of two or more different types of elements. It's still a pure substance, and we'll talk more later about what makes it pure. But it's because it's not just uniform, it's like every particle is identical to the particle next to it, right? And all of them are all identical. Exactly. Exactly. So a compound, it's a pure substance because all the particles are the same, but those particles are made of two or more elements bonded together. So you can have covalent compounds where they share their electrons, or you can have ionic compounds where one gives the electrons and the other takes them. So let's take a look at these two types of molecules. We have molecules of elements. It's a molecule, so it has two atoms. And they are bonded together by a covalent bond. This bond right here, in between, that represents one pair of shared electrons, or you could say two electrons, okay? So that bond represents a pair of shared electrons. So we have I2, Phosphorus has a tendency to form P4, which forms like this little triangle shape, which is kind of cute, like a little pyramid almost. And then sulfur has a tendency to form S8, an S8 molecule, which kind of looks like a little crown. Yeah? And then we have O2. Do you notice anything different about the O2 and its bonds? It's got how many bonds? 2. And that's called a what kind of bond? Double bond. So if you see 2 lines, what kind of bond is it? Double bond. If you see 1 line, what kind of bond is it? It's not a double bond, it's a single bond. Yes, so when we have this double bond, that equals 2 pairs or 4 shared electrons. So a single bond is 2 electrons, a double bond is 4 electrons. And all of those molecules on the left represent elements. They are not compounds. How do I know that O2 is not a compound? Tell your partner, how do we know that O2 is not a compound? I think it's caffeine. I could be wrong, but I think it's caffeine. So how do we know that O2 is not a compound? Compounds are made of 2 or more elements, and oxygen is made of only 1 element. It's only made of oxygen, so it is not a compound. Now, we can have our elements of compounds. We have our covalent bonds here. Water is an oxygen with a single bond to a hydrogen and a single bond to another hydrogen. We have CH4. Do you guys know the name of CH4? CH4 is worth knowing. It is known as methane. And it's the stuff that comes out of these gas pipes. Yes? Also, cows produce a lot of methane. Yes. I said it. I did. They do. Cows, lots of methane. And then this last one here, C8H10O2N2, I think, but I could be wrong, but I'm just going to pretend that I'm right. I'm going to say it's caffeine. Okay, I think that is a caffeine molecule. So you can have elements that, you can have compounds that are really simple, and you can have molecules of compounds that are very complex. And in fact, there is a molecule in your body, well, several of them, but there's a molecule in your body that if you were to stretch it out, it would reach from here to Jupiter. Do you guys know what it is? DNA. Yeah. Okay, so it can be super long. Now, you will notice that these models are made out of a ball, various balls, and they are made out of sticks. So we give this name of this kind of model is called the ball and stick model. Yes, there's balls, there's sticks. It's called the ball and stick model. Another way to represent them, which is more realistic, is what we call space filling models. Because it actually is more representative of this actual space that they take up. But you'll notice if they sort of become smushy on top of one another and it's hard to see each individual atom. And you can imagine if we did something like complicated like caffeine without the nice little sticks in between, you'd be like, okay, and what do I have now? And they'd all be overlapping and just hard to look at. So that's the reason why we often will look at a ball and stick model as opposed to a more realistic space filling model. You don't have to write that down, but I felt like writing it down. Okay, ions. So we've done with atoms, we've done with molecules, and now we are moving on to ions. Ions actually never, ever, ever exist on their own. They always exist as a part of an ionic compound. Monatomic ions. Do you remember what mono meant? Mono means one, and if it's monatomic, that means one atom. So we could draw a monatomic ion here. As long as it's just made of one atom, it doesn't matter what the charge is. Okay, the mono refers to the atom. They kind of look like O's, don't they? So I'm going to shade them in so they don't look like O's. There we go. Okay. Polyatomic ions have two or more atoms, and this is where it gets a little weird. They're actually bonded covalently to each other. So they're almost like little molecules with a charge. Okay, so we might have, for example, nitrogen with a covalent bond to a hydrogen and a covalent bond to a hydrogen and a covalent bond to a hydrogen and a covalent bond to another hydrogen. And all together, this thing has a +1 charge. And that is the NH4 plus ion. Do you guys know the name of NH4 plus? Starts with an A. Ammonium. Okay, so that is a polyatomic ion because it's not just made of one atom, it's made of poly means many. So it is a many atom ion. Now, we already talked about cations, which are positive, but we didn't talk about what kind of element forms positive ions. It's always the metals. Metals always form cations when they form an ion, whereas your nonmetals always form negative ions. Oh, look at that. Isn't that nice? Nonmetal starts with N and negative starts with N. Okay, so your nonmetals form negative ions, your metals form positive ions. How much of this is brand new and how much of it is like kind of ringing bells? Does it sound familiar? Maybe in the past somewhere? Yeah. Okay, it might have been a while. Okay. So here we have some monatomic ions. We have monatomic metal cations. So we have sodium, which is Na+, and you'll notice that sometimes we put the charge inside the atom, and sometimes we put the charge outside the atom when we're drawing a picture. That just really depends on the artist's preference. Okay, we have chloride. And what's the name of the O2 minus ion? Oxide. It's the oxide ion. So when we turn nonmetals into anions, their name changes to "ide" at the end. But when we turn metals into cations, we just say we have a sodium ion. Nothing happens to the name. And if we put sodium and chloride together, what do we get? We get sodium chloride, which is salt. And here we have some polyatomic ions. There's not actually very many polyatomic cations. There's only 2 of them. One of them is called ammonium, which we just looked at. And if we look at the ball and stick model, it's easy to see that we have 4 hydrogens and 1 nitrogen. Even the space filling model isn't too bad for that one. Okay. Now, I have a nonmetal stuck to a nonmetal. What kind of bond is that? What kind of a bond do we have between N, which is a nonmetal, and H, which is a nonmetal? That is a covalent bond. Always, when you have a nonmetal and a nonmetal, that's always going to be a covalent bond, which is kind of funny, right? Because it's a covalent bond inside an ion, and that ion is going to go and form an ionic bond with a different ion. Okay, so bonding is more complicated than we led you to believe in grade 8 and 9. Yeah? And in fact, you can see a lot of these polyatomic ions. What other kind of particle do they kind of look like? Polyatomic ions kind of look like molecules, yeah? They look like molecules, but they have a charge, either positive or negative. So polyatomic ions are essentially like little molecules, but they have a charge, okay? Now there's Mercury insists on being its own weird little self. Yes? All of your metals are solids except for who? Mercury. And there's only two polyatomic ions. One is ammonium, and the other one is mercury 1. Do you guys remember what this Roman numeral means in the brackets? What does a Roman numeral in brackets beside a metal name tell you? It tells you the charge of the ion. Okay, that tells you the charge of the metal ion. Okay, and mercury insists on being weird because normally if I said I had copper 1, right, if I had copper 1, it would look like a copper atom, but it would have a +1 charge. Yes? Pretty straightforward. Mercury, however, insists on being difficult, and it actually bonds with one mercury 1 ion bonds with another mercury 1 ion, and I'm not entirely sure if that bond is metallic or if it's covalent or what. Okay, so I'm afraid I can't tell you that. But what I do know is when you put 2 + 1 charges together, what do you get? You get 2 plus. So the mercury 1 ion is actually written as Hg22 plus. And when I give you your chart of polyatomic ions, it is there to remind you, but don't get too wound up about it because I don't give you mercury 1 very often. It's sort of like one of those rare instance kind of things, and you can mostly just ignore it. And if you don't need to get 100% in the course, if you're okay with 99%, you can just ignore it altogether. Okay? So that's the story with mercury. It's a funny one. And finally, we come on to our fourth type of particle. What were the other three types of particles we had so far? We started with, what's the simplest kind? Atoms. And then what did we have? Molecules. What kinds of elements are molecules made from? They're made from nonmetals. Molecules are made from, just said it, molecules are made from nonmetals. What are molecules made from? Okay, we're all gonna stand up. Everyone stand up, stand up. We're gonna stretch, high up in the air. Okay, and now we're gonna tilt over to the left. And we're gonna tilt over to the right. You okay? Little head rush? You gotta sit down. You're not gonna pass out on me, are you? Yeah, okay. If you are about to pass, and then if you want to, you can do this where you put your arms on the desk and you just kind of make a table of yourself. Yeah? Oh. Okay. And now we're gonna do this one. Oh, stretch back there. We should do this every day. I could totally do this every day. Oh. All right. Formula units. Formula units are single units of ionic compounds. So formula units are like molecules, but for an ionic compound. When you have an ionic compound, what is it made of? What types of elements is an ionic compound made of? And when I say types of elements, what are the two main types? Nonmetals and metals. And what are ionic compounds made of? Nonmetals and metals. So it's a metal plus nonmetal. And when you put those together, you get a formula unit. If we have a covalent compound, what are those made of? Nonmetal plus nonmetal. And those don't make formula units. What do they make? Molecules. So ionic compound, metal plus nonmetal, formula unit. Covalent compound, nonmetal plus nonmetal gives us a molecule. Okay. Now a formula unit is a pretend idea. Can you imagine finding some salt and having only a single sodium and a single chloride? How big would that crystal be? Like, would you be able to see it? No, it would be so small you couldn't see it. Salt just doesn't exist like that. Anywhere where there is like, I don't even know where you could go on Earth where you would find only one sodium ion and one chloride ion that could get together and make a little partnership of two ions holding hands together. There's always going to be more of them, and every time you have one that's near a bunch of others, they will click into place. Yeah? So if I had the green ones are negative, the gray ones are positive. If I had another positive ion, it would click into place right beside if I had a negative, it would click into place right beside the positive. If I had a positive, it would click into place right beside the negative. Okay, so you can never really have a formula unit. It's kind of just made up. What did I do with my stylus? Well, you guys might be in luck. Maybe I can't tell you anything more. Right there? Oh yeah, thank you. Okay. Do we remember the ionic crystal lattice? Yes? Alternating positive and negative. A single unit of that is called the formula unit, but it doesn't really exist. Okay? Very often, you will see an ionic crystal lattice, but they won't label the positive and the negative. So what it would look like is like that. You should recognize that regular alternating pattern. This is not a mixture. Okay? You should recognize that what you've got is you've got probably all of these are negative and all the other ones are positive. Even if they're not labeled that way. Okay, so that's a little bit tricky. Yeah, and you very often you would have like if they're showing it really properly, one of the ions is going to be bigger than the other. Usually the negative ion is larger because it has gained electrons, so it becomes larger. The positive ion has given away an electron, and so it actually loses one shell of its its valence shell is now empty, and so it has become smaller. Yeah. So usually the metal ions are smaller and the non-metal ions are bigger. Okay. And now there are some questions. And I think it would be nice if you did, not the whole thing because it's really long. What if we did 2 pages of it? So like 96 and 97. Would we be good with that? That sounds like baby homework. That sounds like grade 9 homework. How about we do 95 to 97? Okay, there you go. There are bugs all over this school. There's bugs everywhere. There's those. Do you know the bugs that are everywhere these days? Yeah, there's like one here. And I'm like, oh, I gotta get rid of it. Yeah, the stink bugs.